This is the instrument we'll use. It's the commercial brand name is BAR. It's a bar bomb calorimeter. So basically, it's a stainless steel shell, and we have a stainless bucket inside. And if we take a look at the bucket there, it's one gas outlet. So this one is a gas outlet. We use this one to let the oxygen get in. After we fill calorimeter with oxygen, we'll shut off the valve, and then we use these two are electrodes. We use these two electrodes to pass on electrical signal to start the fuse, and then make the benzene or TTCC burn inside. You see the bucket there. We'll fill the bucket with water, and we essentially measure the temperature change in that water. You can see here there are one gas inlet, and there are two connectors to the electrode. This one is slightly different from the schematic showing here, because the stirrer right now is not on top of the BAM, it's at the bottom of the BAM. So you don't see the stirrer. So in this case, you don't see the stirrer, right? And the thermometer here, we show a thermometer here, and you don't see the thermometer as well, because in this instrument setup, the thermometer is inside the bucket at the bottom of the bucket. So you won't see it from top. So we put larger amount of oxygen through the gas inlet, and then start the fuse through the electrical wires, through these two electrodes. And then the chemistry reaction will occur inside, and heat will generate it, and heat will be absorbed by water, and will measure the temperature rise. In the handout, there are two processes in BAM calorimeter. One is called isothermal. The other is called a adiabatic process. So the isothermal process is a type of a thermodynamic process in which the temperature of the system remain constant. So temperature of system remain constant. The temperature will have a little rise. That's due to the stirrer. So the stirrer is inside rotating. That's passing some mechanical energy into the water, into the BAM as well, right? So the temperature will be increasing slightly over time. And during the chemical reaction, there'll be a sudden temperature rise, right? And after that reaction, because the system, so look at the definition, the temperature of the system remains constant. Since because the system should remain at the constant temperature, then the temperature will gradually drop towarding the constant temperature. In the case of adiabatic process, in the beginning, since there is no heat transfer from surroundings, the temperature should be a constant. And suddenly there is a chemical reaction, so a sudden rise of the temperature there. And after the reaction, since there's no heat transfer between your BAM and surroundings, then the temperature shouldn't change after that, because it's extremely difficult to make a no heat transfer between BAM and the surroundings. So most process will be our isothermal process. Well, some of the adiabatic process will be only part of the isothermal process. Assuming if the heat transfer is slow enough, then the slope of this curve, slope of that curve will be flat enough. So in the short time, we can consider our isothermal process as an adiabatic process. What should we consider in our case? we look at the schematic of our bond colorimeter. The bucket just have some airspace surrounded. There is air in it. It's not vacuum. So the air will carry out some of the heat away, right? So in our case, it's going to be isothermal. This is the data we actually got from the bond colorimeter. As we can see, if you just look at a short period of times, for example, if you just look at here, and the temperature actually did not drop until after 1500 seconds. So if you consider a long range, then you will see a better isothermal curve. Okay, if you just look at the short range, it'll be very similar as an adiabatic process. Okay, so in our data analysis, you will be looking at the delta T at the center of that curve. And there are different methods to look at the delta T for the isothermal process. And in our case, I just want you to write the trend line for this one and that one. So beginning and at the end. So when you figure out the trend line and take the difference between the trend line and try to make sure in your schematic, try to make sure the area here, this area is similar as this part. As long as you do that, then you can figure out the delta T in the center there. There are more detailed mathematical process in terms of how to get the equal area of delta, then you can figure out the delta T. So for the purpose of this experiment, I don't need you guys to go through all the mathematics. So I just want to, you get approximately the same area, then you can say, okay, this is my delta T here.